Yeah, I have a question. I,
Mhm.
I was wondering, have you considered those matrices that are essentially talking to each other? That is, you take a bunch of blocks of matrices like you do, but instead of just uncoupling them, coupling them a bit with a tiny amount of rows for both of them, and see if there is some way that there is a better sketching coming out of this as opposed to the one you're currently doing.
So let's see. Let me open the presentation again. So just want to make sure that I understand the question. So we have
Yep.
this figure, right?
Yep.
Right. So can you repeat the question again?
So basically, when you're looking at this matrix, it's being done by block.
Yeah.
There are certain matrices that are coming up in compressed sensing where you basically can get, let's say, the end of the first matrix
Oh,
that
oh,
goes
oh,
all the
oh.
way to the second matrix.
Got
And
it.
the first part of the second matrix essentially goes into the first matrix.
I
So they
see.
essentially are coupled in some very
I
tiny
see.
fashion, but they are coupled.
Oh,
And
I see.
somehow the whole coupling allows some information to essentially travel back and forth. But if that's not really
Mm-hmm.
useful, or if you
Mm-hmm.
haven't tried it,
Mm-hmm.
I'm just wondering, right?
No, yeah, that's a really good idea. So, like, if there's overlap between these sketching blocks,
Yes.
maybe we can sort of forego these conditions on the incoherence parameters itself, and that's something that I've not tried, but I think that's something really interesting because what we would then have to do is basically these different nodes will talk to each other a little bit, communicate a few rows here and there.
Yes.
Yeah, no, that's a great idea. I've not tried it, but I'd be super interested in seeing if that helps in better performance in terms of sample complexity.
Well, there was a paper on this back in 2011, actually, that
Oh,
talks
okay.
about this, and so I can point you, or
Yeah.
Jacopo can point you to this. It's basically kind of very interesting because it essentially also had some influence in compressed sensing in a major
Mhm.
way, actually. So
Yeah,
um,
I'd be super interested. Do let me know what the paper was, and I'd take a look.
sure, I'll
Yeah,
do that.
thank you. Yeah.
Any other questions?
Yeah, I have one. So, hi, Rakshith. Thanks for the talk. It was indeed very clear. I was just
Thank you.
wondering because your technique seems so appropriate to like map-reduce kind of computing.
Mhm.
Have you tried it on an actually distributed cluster with Spark or something like that?
No, I have not tried this on a distributed cluster, and that's something that I'm interested in doing. But this paper came out and sort of got busy in other things, so I really haven't tried it. But I think that's a really good thing to do, and will actually lend a lot of support to this paper.
Mm. Yeah. Okay.
Yeah. So if you're interested in doing that, like I'd be happy to work together on that. So,
Yeah, perhaps. Thanks.
Yeah, thanks. In the meantime, I see that Laurent linked to the paper Igor was just mentioning in the chat,
oh,
if you
great.
want.
Awesome. That's perfect.
Yeah, any other question for Rakshith?
I have another.
Mm-hmm.
Hi, thank you again for the presentation. And reading the literature, I saw that many people are using sketching even for logistic regression. And
Sure.
And I just wanted to ask if you think that the localized sketching can be easily extended to the logistic regression.
Yeah, so I definitely think it can be easily extended. So again, there will be another sort of maybe this incoherence parameter shows up, but it might be slightly different than how we have defined for these two particular problems. But once we identify what that the importance parameter should be for the logistic regression problem, I think it can be extended, and I don't think there would be any surprises in terms of the sample complexity performance.
Okay, sorry, a final question.
Yeah, no, for sure, I'm happy. Yeah.
You need to forgive me because, like, among this team, I was the one that spent several weeks on your paper. And,
oh wow, okay, yeah, that's good to know. Yeah.
This is a final one, is maybe a bold question. Like
Yeah.
reading a lot about sketching, I realized that the main trade-off is that sketching works, but of course the technique should be, the random projection should be faster than solving the original problem.
Exactly, yes.
As like LightOn, we think we can like solve this projection time problem. So do you think that once we let's say we do, we provide an hardware that's able to do this initial projection, and I literally speak about S times A in a really fast way. Do you think that that would provide like a big leap forward in the sketching research?
Yes, I think so. And so all of the papers that talk about sketching usually focus on the sketch compute time and try to drive it down. So if there's a way to do it really well, then I think it's a good contribution to the literature. And especially in the paper that I just described, we sort of use these dense Gaussian distributions for these blocks only for the reason that they're very easy to theoretically analyze. And I don't think they have a lot of practical advantage. But if there's a way to compute these sketches quickly, then I think that's going to be a good contribution.
Thank you very much.
Especially because so whenever I give a talk about this paper, I would really like to have like a real-time simulation where I show how long MATLAB takes to solve this ridge regression problem or in the higher dimensions, but also show that it's much faster once you sketch it. But always the bottleneck is writing efficient code to compute that sketch itself. So maybe having this real-time demonstration is very interesting.
Thank you very much.
Sure.
Thank you. Questions for Rakshith? Otherwise, I have one. Okay, silence. So I'll ask mine. Sure. So as Alessandro was saying, we have like our product performs random projections essentially at the speed of light. This is our like punchline.
Sure.
As in, you can perform Gaussian random projections at a speed that essentially is independent of input and output size. So if the input is 10,000 or 1 million, it takes the same amount of time.
I see.
And we can go up to both 1 million in input and output size. The product we have right now available on the cloud, on LightOn Cloud, I think Victor talked with you about that. Performs the random projection, but there is a non-linearity at the end, that is the absolute value squared. We're working to take it away, but still with this device we can do interesting things. And I was wondering if you like at the beginning of the talk, you talk about linear sketching, but how like, do you know how any of this translates to the case where you have a non-linearity? Are there bounds or literature about it?
So no, I haven't come across a lot of literature that does nonlinear sketching. Something that I have come across recently is these linear sketches. We're just using Gaussian random measurements, but they are so these matrices are being learned using neural networks. So there is nonlinearity in the way you learn the sketching matrix, but finally it's again a linear sketch. So I don't know of any theory that studies nonlinear sketching.
Okay.
Yeah.
Thanks.
Yeah.
Any other questions?
So I guess like I have one question, if you don't mind.
Yeah.
So
Sure.
How do you do these random Gaussian projections independently of size, I guess?
Yeah. So
is that something that you're allowed to tell me?
I can tell you.
Sure.
So the idea is to use property of scattering materials. And that is when you shine light through a scattering medium and you acquire the intensity of the output beam, and you have encoded the light that goes through the scattering medium with information in some way.
I see.
Essentially, you can model this physical process as y equal a random matrix complex with Gaussian real and imaginary part.
I see.
Times the input vector.
I see.
And absolute value squared. So
okay.
This is like very broadly how we do it.
Sure,
the details are like, of course,
yeah,
our secret, but
perfect. Yeah, that sounds great. Yeah, I'd be interested in reading more about this.
And yeah, actually, we have a few of these devices on the cloud. On our we have our own cloud that's called LightOn Cloud, and they're available. And we have a program for researchers to use them for free. So I will send you more details about this later, because I think definitely in the work that you do there is a lot of overlap with what's of interest to us, and yeah, I think we can do nice things.
Sure, that sounds great.
Yeah, I don't know if Igor and Laurent want to say something before closing.
Igor?
Yeah, I'm sorry. I just cut my mic just to make sure that I'm not cutting the flow of the discussion. It looks super interesting. I mean, I love what you guys are doing. Obviously, I've been following at least a bit what Mark has been doing over the years, as well as Justin's. So I'm not surprised about the type of subject area you are in. Are there any particular use cases that you are getting into these days, or is it still a generic linear algebra type of randomization of sorts? Are you getting into use cases of sorts?
Yeah, so we are slightly going in this direction of antenna array processing. So there are a lot of interesting problems there where the scale of the data is just massive, and solving these problems after the dimensionality reduction is very interesting to them. So I think one problem we've been looking at is direction of arrival estimation. So you have an antenna array, and you have like maybe 5 sources sending you signals. So the idea is that each source is associated with a subspace of its own. So it just directly translates to this problem of, can you identify the subspace after you sketch? So that is one area that we are actually like working on right now. And the other area that we are also excited about is, again, people have these distributed sort of robots going into space or even underwater, collecting data and trying to talk to each other. So even there, I think the constraint is you have a lot of onboard computation on each of these nodes, but not a lot of communication bandwidth. So these two areas even though these methods are very generic right now, like we're trying to adapt them to these applications actually.
I see. Okay.
Yeah. So mostly in sensors and sort of what we call as these ML at sensor level applications.
I see. Okay.
Yeah.
And so stupid question on the technical side of things. In the sketching that you did for those matrices that were sparse, the PhD matrices, I don't know how you call it these days, but
yeah,
the DFFT ones.
Sure.
Which particular ones were you using? I mean, is it just a bunch of Fourier and then random diagonal and then back into a Fourier, or is it a little bit more complex than that?
It's actually much simpler than that. So for some reason, MATLAB's implementation of these randomized Hadamard transforms are not efficient. So all the papers theoretically claim that these Hadamard transforms are as fast as FFT. So what we did was we just used a plain FFT. So anything that's being practically used in other sketching papers is going to be at least more expensive than what we compared with. So we just used a plain vanilla Fourier transform without adding any diagonal random matrices or Hadamard transforms. So so that way I think we are sort of comparing our method to whatever is the best possible.
I see. Okay.
Yeah. And the intention was to just show that it's competitive and not sort of focus on the exact fast technique that is existing in the literature.
At those large numbers of elements, I think I remember there was a paper by, I can't remember exactly who was essentially pointing out that when you were multiplying by, when you were using a very large system that you're trying to invert and everything, if you were at a very large scale, the rounding error was essentially killing you. And so you essentially had to go for not 32 bits, but 64 or 128.
I see.
And so there was a sense in that paper that you could essentially do the sketch of the actual big prime and solve the smaller prime with an uncertainty a bit like your epsilon that you're mentioning. But that epsilon was just smaller than the round of error that you would be getting into solving the actual system in the first place. Have you encountered something along those lines in the line of work you've been doing so far?
Not
That
really.
he's trying to solve the actual system, and then the round off is essentially just changing everything. And so,
no, I don't think I have run into those problems on my end. But again, I think I've been just doing some simulations in MATLAB and Python, which are pretty high level. So I don't, yeah, but no, I don't think I've come into run into those issues.
Okay.
Yeah.
So you've been trying to solve the actual prime without the sketching? I mean, in order to get the epsilons. Okay.
Exactly. Yes.
Okay.
Yeah. And I've been staying within limits of what I can do. So that's why maybe I've not run into those problems.
And so what's the longest you've been spending in terms of getting to solve the actual system, not the sketch one? How much time does it take?
Maybe within like in the order of tens of minutes.
Okay.
Yeah, not more than that. Yes.
And then with the sketching, essentially, you get down to much lower.
Much lower, yes.
Okay, because of DFFT and everything. Okay.
Exactly. Yeah.